Welcome, curious minds. Today we're cutting through the noise, the information overload.
And getting right to the core.
Exactly. Getting to what's important, maybe even uh, peering into the future a bit.
With surprising clarity, hopefully.
Yeah. We're doing a deep dive into large language models, LLMs, but maybe not just the chatbots you're thinking of.
No, we're going deeper, looking at their, well, really transformative uses.
Specifically in two critical areas:
Yeah.
forecasting, predicting future stuff, trends, events.
And anomaly detection, so spotting the unusual, the outliers, things that might be critical.
And look, this deep dive, it's basically your shortcut.
We've done the legwork, gone through a really comprehensive systematic literature review on this.
So you get the essentials,
Yeah.
the current state, the challenges, what's next for LLMs in these fields.
The goal is for you to walk away with some significant actionable insights. Fast.
Okay, so let's set the stage. LLMs, what exactly are we talking about here? Foundational stuff first.
Right. So at their core, LLMs are advanced deep learning models. They take input text, usually.
And predict what comes next, word by word or token by token.
Exactly, token by token. But what really sets them apart is the scale. Huge scale.
How huge are we talking?
We're talking tens, hundreds of billions of parameters
Yeah.
trained on just enormous data sets, gigabytes, terabytes of text and data.
And we hear names like BERT, GPT, Llama May 2, Mixtral. These are mostly based on the transformer architecture, right?
That's right. The transformer is key. Its self-attention mechanism, that's really foundational.
It lets the model figure out which parts of the input are most important for context.
Precisely. Which is critical when you're dealing with these massive amounts of data.
Okay, let's unpack this evolution a bit. I
Yeah.
mean, machines understanding language, that idea goes way back. Turing test, 1950s.
Right. And for a long time, early deep learning, like LSTMs, CNNs, they focused on narrower NLP tasks, intermediate steps.
But then came pre-trained language models, PLMs. That was a real shift, wasn't it?
Huge shift, this two-stage process, pre-training on a massive general data set first.
Learning the general rules of language, sort of.
Yeah, universal patterns.
Yeah.
Then the second stage, fine-tuning on smaller, specific data sets for particular tasks.
And that improved accuracy and generalization, the
Well-
ability to handle new stuff.
Dramatically improved both, made them much more flexible.
Okay, here's where it gets really interesting for a lot of people, the GPT series. That really pushed things forward. GPT-1 showed early zero-shot learning potential.
It did, early glimpses.
Yeah.
Then GPT-2, trained on even more data, unlabeled data, showed it could do many tasks pretty well without specific fine-tuning.
Just based on that massive pre-training.
Exactly. Showed the power of scale.
But GPT-3, that was the leap to few-shot learning, in-context learning.
Yes. That was a game changer. You give it instructions and maybe just a couple of examples in the prompt itself.
No retraining the whole model.
No parameter updates needed.
I got it.
Like showing a smart intern, as you said. High generalization.
But it also surfaced issues, right? Biases from the training data, things like potential for fake news.
Definitely. Those societal implications became much clearer, which led to refinements.
Like Instruct GPT or GPT 3.5. The focus shifted to alignment.
Right. Aligning the model to be helpful, honest, harmless, using supervised fine-tuning, SFT, and reinforcement learning with human feedback, RLHF.
And interestingly, it performed better than the bigger GPT-3 sometimes, but with fewer parameters.
Yeah, 13 billion versus 175 billion for GPT-3 showed alignment was really powerful.
And then GPT-4 scaled up massively again, over 1 trillion parameters.
Yep. Refined the RLHF process, but the big step was multimodality.
Meaning it could handle more than just text.
Right. Processing images and text input to generate text output, plus better filters for inappropriate content.
So when you trace that evolution, understanding context, few-shot learning, multimodality, you can see why forecasting and anomaly detection seem like such a natural fit.
Absolutely. It starts to make a lot of sense.
Can you elaborate on that? Why are they so uniquely suited for these tasks?
Well, think about what they are. Forecasting. Predicting future data points based on past patterns. Anomaly detection. Spotting outliers. Deviations from the norm.
Both rely on sequence analysis, right? Especially time series data.
Exactly. Time series, timestamp data sequences collected over time, showing trends, cycles, all that. LLMs are fundamentally sequence processors.
So give us an example. Cybersecurity.
Perfect example.
Yeah.
Anomaly detection could flag weird login patterns, maybe indicating a breach.
Or in industry, Manufacturing?
Could be unexpected sensor reading spike, maybe predicting equipment failure before it happens.
It feels like LLMs are almost purpose-built for this kind of sequence pattern recognition.
Precisely. And the opportunity is huge. They can augment, maybe even revolutionize these areas, bridge that gap between language processing and predictive analytics.
Okay, let's get practical. How are LLMs actually doing this? Predicting, detecting. Let's start with forecasting.
Okay, forecasting. They're using those learned patterns, linguistic and contextual, from historical data. And we see a couple of main strategies emerging.
What's the first one?
One way is to kind of translate numerical data into text so existing LLMs can process it.
Wait, you feed numbers into a language model? How?
Yeah, models like Promptcast. They turn numerical time series into textual prompts. So the LLM reads the trend like a sentence.
Huh. That's clever.
And others have shown you can reprogram an LLM, like Llama 2.7b, for time series forecasting, adapting it without full retraining.
So you're leveraging the language pattern skills for numerical data. What's the other approach?
The other path is building specialized models, still transformer-based, but designed specifically for time series.
Like tempo.
Exactly. Tempo treats past data points like prompts in a conversation. It's like asking ChatGPT about numbers.
So adapting the core architecture itself.
Right. Both show the flexibility. And it's not just general time series. Think traffic flow prediction for autonomous cars, or even clinical predictions in healthcare. Really specific stuff.
Okay, shifting gears to anomaly detection. Finding the outliers. Crucial for security, quality control. How are LLMs used here, especially with time series data?
Well, some researchers, like Dang et al.,
Yeah.
have used BERT-based models. They treat it like text classification.
Classifying a sequence as normal or anomalous.
Pretty much. And what's interesting is they get good results even with small amounts of labeled anomaly data. Shows good generalization.
And you mentioned log analysis earlier. That seems like a huge area for LLMs. System logs. They're messy, right?
Oh, incredibly messy, unstructured, noisy, massive volume. Really hard for traditional methods.
So how do LLMs cut through that?
Because they excel at finding patterns in unstructured text. Models like BERTlog or LanoBERT treat log entries like sentences, capturing semantic meaning, context.
They understand what the log is saying.
In a sense, yes. Others like LogPrompt use prompt tuning, guiding the LLM to focus on relevant log info.
And I heard about LogFit. That one sounds revolutionary because it doesn't need labeled data or templates.
Exactly. That's a big deal. It uses self-supervised learning on normal logs. It learns what normal looks like by itself.
So it can adapt to messy, real-world logs where anomalies are rare and maybe unlabeled.
Precisely. Very agile. And Neuralog goes even further. It skips log parsing altogether.
Directly from the raw log message. How does that help?
Avoids parsing errors, which can sometimes hide or misinterpret anomalies. Gets straight to the semantic insight.
Wow. So LLMs bring serious intelligence to these difficult data types. And this extends to things like microservices too, real-time detection, even fixing problems automatically.
Yeah, platforms like Adharma are doing that, focusing on real-time anomaly detection and auto-remediation to cut downtime. It's really moving fast.
Okay, so we see what they can do. But let's dig into the how. What are the core techniques researchers use to make LLMs perform these tasks?
A really key one is prompt-based learning, crafting specific instructions or templates for the input text.
To leverage the knowledge already in the pre-trained model?
Exactly. It allows few-shot, sometimes even zero-shot learning without touching the model's core parameters. Very efficient.
And then there's fine-tuning, taking a general model and training it a bit more on specific data.
Right. Adapting it, making it a specialist for a certain task. Much cheaper than training from scratch.
We also hear about zero-shot, one-shot, few-shot learning. Can you break those down quickly?
Sure. Zero shot. The model predicts something it's never seen explicit examples of, just based on related knowledge, like describing a new bird species.
Okay, one-shot.
Trained on just one example of a new class. Sees one daisy, can then spot other daisies.
And few-shot is just a small handful of examples.
Yep, exactly. More than one, but still not a lot of data.
And what about model reprogramming? That sounds different.
It is quite clever. You repurpose a model for a totally new task just by changing how you feed it the input.
Without retraining or fine-tuning?
Correct. Lower computational costs, like giving an old tool a new jig to do a different job.
So, okay, amazing potential, clever techniques, But what about the real world? Deployment isn't always easy. What are the big challenges?
Definitely not always easy. A major one is just the complexity of time series data itself.
Seasonality, trends, external factors like economics or weather.
Exactly. All these intricate patterns and influences, it's hard for any model to capture all of that perfectly.
So the solution involves better models, more data.
Better models, yes. Models that can learn from diverse data, integrate external context, handle non-linear stuff. It's a big data science challenge.
And especially for anomaly detection, you mentioned labeled data is scarce. Anomalies are rare.
Huge issue. Getting enough labeled examples of weird is tough and expensive.
So how do you train a model to find something you barely have examples of?
That's where techniques like transfer learning come in pre-trained broadly, fine-tuned narrowly. Also, semi-supervised methods, data augmentation, trying to make the most of limited labels, unsupervised methods are key too.
What about gaps? Missing data in time series? Sensor fails, collection hiccups.
Yeah, another common problem. You need robust ways to fill in those gaps, imputation methods that work well with the LLMs. Still lots of research happening there.
And the noisy, unstructured text data like logs? Even with LLMs, getting signal from noise is hard.
It is. LLMs will automate feature extraction, which is great.
Yeah.
But you still need careful tuning, validation, maybe bringing in external knowledge bases to really nail it.
Then there's the reliance on huge historical data sets. That raises flags, right? Bias, data quality. Will the past predict the future?
Absolutely. Big questions. Is the data representative? Is it biased? Does history even hold the right patterns for the future, especially for rare events?
Solutions there seem to focus on diversity, augmentation.
Yeah, data diversity, augmentation, synthetic data, transfer learning, active learning, few-shot methods. Also, models that can update dynamically with new data, not just rely on a static past.
And generalizability. A model trained for, say, finance data might not work well on medical data.
Often, yes. That cross-domain generalization is still a hurdle. Many of the data solutions help here too, but it's a factor.
And the sheer compute power needed. These things are beasts.
They are resource hogs. Training and deployment is expensive.
So optimization is key, making them smaller, faster.
Definitely. Techniques like pruning, quantization, knowledge distillation, also more efficient architectures, specialized hardware like GPUs, TPUs, and smart use of cloud and edge computing.
And finally, a really critical challenge. Model hallucinations and just knowing their limits.
Yeah. LLMs can sometimes generate stuff that sounds plausible but is just wrong, or confidently state things beyond their actual knowledge base.
And dealing with that, how do we ensure they're trustworthy?
That's a major ongoing research area. Model explainability, trustworthiness.
Oh.
It requires continuous innovation to make them reliable for critical tasks.
Okay, that's a lot to grapple with. So, given all these complexities, how do we actually measure success? How do we know if an LLM is doing a good job at forecasting or anomaly detection?
Great question. Metrics are absolutely essential. Quantitative ways to evaluate performance, compare models.
Let's start with forecasting, measuring how far off the predictions are.
Right. You have things like mean absolute error, MAE, the average size of the errors, regardless of direction.
Then mean squared error, MSE, which squares the error.
Yep. So larger errors get penalized more heavily. And RMSE, root mean squared error, which is just the square root of MSE, bringing the units back to normal, making it easier to interpret.
What about percentage errors, like MAE?
Mean absolute percentage error. Good for interpretation, but tricky if actual values are near zero. There's also some MAPE, symmetric MAPE, which handles that better.
And MSE, scaled error.
Absolute scaled error. Compares the model's error to a simple naive forecast like tomorrow will be the same as today. Good for comparing across different data scales.
And the OWA, overall weighted average.
Yeah, that combines MAE and SEM-E. Used in big forecasting competitions like M4, gives a comprehensive score against a baseline.
Okay, now for anomaly detection, the focus shifts, right?
Yeah.
It's about finding the outliers, but also not crying wolf too often.
Exactly. It's a balancing act. We talk about true positives, true negatives, false positive, false negatives.
Remind us, true positive is finding an anomaly correctly.
Correct. True negative is correctly identifying normal data.
False positive is a false alarm calling normal data anomalous.
Right. Can be costly depending on the context.
And false negative is the dangerous one missing a real anomaly.
Exactly. Often the most critical error to avoid, like in security or safety systems.
So metrics like accuracy, overall correct predictions, might not be the best here if anomalies are rare.
Right. Accuracy can be misleading. A model predicting normal all the time could have high accuracy but be useless.
So we look at precision, Of the things flagged as anomalies, how many actually were?
Yes. Crucial if false alarms are expensive or disruptive.
And recall true positive rate. Of all the real anomalies, how many did we catch?
Vital when missing an anomaly is unacceptable.
And the F1 score tries to balance precision and recall.
Exactly. It's the harmonic mean. Very useful for these imbalanced data sets where anomalies are rare.
Finally, AUROC, area under the ROC curve.
Area under the receiver operating characteristic curve. It measures how well the model distinguishes between normal and anomalous cases across different decision thresholds, a good overall measure of discriminative power.
So it's always about balancing sensitivity catching anomalies and specificity avoiding false alarms based on what the application needs.
Precisely. The trade-offs depend entirely on the context.
So looking ahead now, where is this all going? What are the exciting future trends for LLMs in forecasting and anomaly detection,
Well, one huge trend is the integration of multimodal data,
beyond just text?
way beyond. Combining text with visual data, audio, sensor readings, getting a much richer, more holistic view. Think medical imaging combined with patient notes, or autonomous cars using cameras and linguistic context.
That sounds powerful for more nuanced predictions and detections.
Definitely. Another big push is towards real-time processing and edge computing.
Getting the models closer to the data source, reducing delay.
Exactly. Less latency, faster insights, especially critical for things like fraud detection or industrial control.
And there's a growing awareness of the environmental cost, right?
Yeah.
Sustainable AI.
Absolutely. Energy efficiency is becoming a major concern, optimizing algorithms, hardware, practices to reduce the carbon footprint of these massive models.
Makes sense. And finally, you mentioned interdisciplinary collaboration, bringing different fields together.
Crucial. Statisticians, machine learning experts, robotics engineers, ethicists, they all need to work together. That's how we'll get robust, reliable, and ethically sound solutions.
So reflecting on this deep dive, we've covered a lot. The potential of LLMs in forecasting, in anomaly detection. It's immense.
It really is. From the basic mechanics to these very specific, sometimes surprising applications, they can parse data and find patterns in ways we couldn't before.
But the challenges are real too. Data issues, compute costs, reliability.
Significant challenges, no doubt. But the pace of innovation in finding solutions is also incredibly fast. The future directions are genuinely exciting, feels transformative.
Absolutely. Which leaves us with a final thought for you, the listener. As these LLMs get better and better at predicting the future, at spotting the unusual, how do you think this reshapes our own role in making decisions? What new responsibilities do we need to embrace to make sure this powerful technology serves society well? Something to think about.